We have sent probes to the surface of Mars. We have imaged galaxies billions of light-years away. And yet, the floor of the ocean that covers more than 70% of our own planet remains, in large measure, a place we have never seen. That is not a poetic exaggeration. It is a documented gap between what humanity expects of its own technology and the reality of what the deep sea actually demands. The ocean is not simply large, it is the dominant feature of this world. Salt water covers approximately 70.8% of Earth's surface, holds 97% of the planet's water, and harbours most of its animal and protist life. It is the origin of photosynthesis, and it still supplies roughly half of the atmospheric oxygen every living thing on land depends upon. When scientists study its floor through the discipline of marine geology, they are working to understand the history and structure of a place that is, in practical terms, more remote from direct observation than the near side of the Moon. Marine geology draws on geophysics, geochemistry, sedimentology, and paleontology, and each of those disciplines runs, eventually, into the same wall. You cannot map what you cannot reach, and reaching the ocean floor is genuinely, consequentially, hard. The difficulty begins with scale. The ocean is not a uniform shallow basin. It is a landscape of abyssal plains, mountain ranges longer than any on land, trenches that descend to depths where pressure is measured in hundreds of atmospheres, and ridge systems that are geologically active. Light does not penetrate to those depths. Radio waves do not travel usefully through seawater. The tools that make remote sensing easy above ground, satellite radar, optical imaging, aerial survey, are stopped at the ocean surface as effectively as a wall. What does reach the seafloor from above is sound. Multibeam sonar, mounted to research vessels, sends acoustic pulses downward and times their return. But sound travelling through kilometers of water column is subject to variation in temperature, salinity, and pressure, each of which bends and scatters the signal. The deeper the target, the wider the beam footprint on the bottom, and the coarser the resulting resolution. Mapping the deep ocean floor from a surface ship is, in spatial terms, a slow and imprecise process. A vessel must physically sail over every square kilometre it intends to map. The ocean is vast. The fleet of research vessels capable of this work is not. This is where expectation and reality diverge most sharply. The divergence is not theoretical. It has consequences that arrive suddenly, in real emergencies, in real time. On the 1st of June, 2009, Air France Flight 447 crashed into the mid-Atlantic Ocean, killing all 228 passengers and crew on board. The aircraft went down over open ocean after inconsistent airspeed indications and resulting miscommunication between the pilots led to an unrecoverable stall. The Brazilian Navy recovered the first major wreckage and 2 bodies within 5 days. But the aircraft's flight recorders, the black boxes that carried the definitive record of what happened in those final minutes, were not recovered from the ocean floor until May of 2011, nearly 2 years after the accident. The recorders were there. The searchers knew approximately where the aircraft had gone down. The ocean floor simply did not yield them easily because the floor in that region was not well mapped, the search area was large, and the tools available to find small objects on a complex, poorly charted bottom were limited by the same physics that constrain all deep ocean work. That case, difficult as it was, at least had a known crash site region and a defined search perimeter. The disappearance of Malaysia Airlines Flight 370 on the 8th of March 2014 presented a different and more extreme version of the same problem. The search that followed became the most expensive aviation search in history, extending across Southeast Asia and into the southern Indian Ocean. Part of what made that search so difficult, and what shaped its outcome, was that the seafloor of the southern Indian Ocean in the relevant search zones was, at the time, the aircraft disappeared, incompletely mapped. Conducting a detailed search for wreckage first required conducting detailed surveys of the bottom itself. The search for a missing aircraft became, of necessity, a mapping expedition. The ocean floor had to be discovered before it could be searched. These two incidents are not anomalies. They are illustrations of a structural reality. The gap in ocean floor knowledge is not an abstraction confined to academic marine geology. It surfaces whenever something is lost at depth, whenever a submarine cable fails and its exact routing must be confirmed, whenever a tsunami warning system needs to place a sensor on a particular ridge feature, whenever a drilling operation must understand the sediment beneath a chosen site. The ocean floor's incomplete map is a consequential fact that touches aviation safety investigations, environmental monitoring, resource assessment, and the basic scientific understanding of how this planet works. The instruments that exist to address this gap are genuine and capable. Autonomous underwater vehicles can carry high-resolution sonar to within meters of the seafloor, producing imagery of startling detail. Remotely operated vehicles can retrieve physical samples and photograph geological features. Marine geology integrates all of this: the geophysical survey data, the sediment cores, the chemical analyses, the fossil records embedded in seafloor sediment, into an increasingly detailed picture of how the ocean floor formed, how it moves, and what lies upon it. The discipline is not stalled, it is advancing. But the ocean is the ocean. It covers 70.8% of the Earth. The logistical demand of physically transiting every unmapped kilometer with an instrument capable of resolving the bottom at useful resolution is simply not yet met. The research capacity that exists, as real and sophisticated as it is, has not closed the gap. What has been mapped in high resolution is a fraction of what remains. The precise question that remains open is this: what does the unmapped seafloor contain in terms of geological features, biological communities, and physical conditions that would change our understanding of how the deep ocean functions as a system? And what would it change about our ability to respond when something is lost there? The honest answer, the only defensible one from the evidence, is that we do not know. Not because no one is asking, and not because the instruments do not exist, but because the ocean is larger than our current capacity to observe it systematically. There is something exact in that. The ocean originated photosynthesis. It governs climate. It holds the vast majority of Earth's living biomass. It is the primary component of this planet's hydrosphere, acting as a reservoir of heat that shapes every weather pattern on every continent. And the floor beneath all of that, the geological foundation of the dominant feature of the world, is a place humanity is still, in the most literal sense, in the process of finding. The instruments are getting better. The autonomous vehicles are multiplying. The data pipelines from research vessels are expanding. Progress is real, and it is documented. But the gap is also real, and the consequences of that gap have already been written into two of the most significant aviation disasters of the modern era. What else is written into the unmapped sections? What geological processes, what biological systems, what physical boundaries, is the question that the next generation of ocean floor surveys will have to answer, one slow acoustic pulse at a time. The deep ocean does not withhold its secrets out of mystery. It withholds them out of physics and scale, and the simple unresolved arithmetic of how much floor there is and how few instruments we have sent to find it.